So sorry about that. For those online, we're going to come back to the membrane systems, talk about that briefly before we start talking about disinfection, and I'm going to pass back some graded work. This is your homework 1 and exam 1, so I'll be doing that for the next couple minutes. One comment though about the exam before I begin. I decided to curve it in a sense. The last problem was granular filtration, and you had not had any real practice with that outside what we did in class, and I felt like that was really not probably fair. So what I did with that problem was I went ahead and scored everything as I would normally, and then I decided I was going to give 70%, 75% of the credit back to you for whatever you missed on that last problem, the granular filtration. So you'll see a number, and then plus a number, and then an underlined number. So that's your curve in effect. Okay. So the average before the curve was a 70, and afterwards it's an 80. So I felt like that was that bumped it up pretty reasonably. So that was the deal. Don't think I have too many comments otherwise. Of course, some of the homeworks were submitted online, so if I just give you back an exam, that's all I have from you physically, and you'd have to let me know if you wanted a copy of the graded file. Okay, I'm just gonna say all the names. I'm close to knowing everybody, but with the masks it is hard, so I apologize. Stephen Tran, Robert Shoup, Julia Henderson, Teresa Brown, Matt Davis, Madeline England, Jesse Sidney, no other than that. Okay. And for anybody that's online or not, did not get their papers this time, be happy to, I'll aim to bring them back in class with me later. One other note before we begin, I thought that they just canceled fall break altogether and that we're just gonna have class Tuesday like normal. Apparently they made it so that we're doing fall break virtually. So I'll just lecture from home where I've never had internet outages. So presumably that should go smoothly. And if it doesn't, I will start the recording and just have the recorded one posted for you. But so that'll be Thursday, and really we're going to start disinfection today. We'll pick back up wherever we leave off today and continue with that. Okay, how did you guys like the guest lecture? Is that interesting? Matt is a fun guy, so hopefully he was entertaining. He's, I think, appreciating the practice standing up and speaking in front of people, because he's admitted to me that that's been something that he's needed to work on. So glad to hear you guys liked it. Any thoughts or anything I should share with them? Well, it'll complement pretty well the disinfection. I normally just touch on some of the advanced oxidation processes, so hopefully that was we'll connect that a little bit as we go through the different disinfection technologies. Okay, so membranes. I think the stream cut out somewhere around this slide. Is that familiar, or was it maybe the slide before? Did you guys, anybody that was watching the stream, do you guys remember where we were? This one? This one? Okay. All right, so we'll pick up here then. Okay, so that's right. So we were talking about essentially driving water through membranes, and the way we do that is adding pressure either on the front end or applying the vacuum on the back end. Of course, if you're taking the vacuum thing, you still have the differential, so you can only vacuum down to 0, and then you just have the atmospheric pressure to deal with. So either way it works is fine. You just have to make sure that you are finding a way to apply the pressure that you need. We call that pressure the transmembrane pressure because really what we're looking at is the pressure across the membrane. So if we have a membrane of some thickness, we could get into the nitty-gritty and measure the pressure right at the edge and compare that to the pressure just on the other side. And that's the transmembrane pressure that we're going to talk about. Membrane scientists will even go so far as to theorize about measuring the pressure inside the membrane and what relevance that might have. So kind of interesting stuff going on there. The flux here, I had some units here I decided were not really a good representation of the flux as calculated by these units. So the flux in general is volume per area per time, and you could translate that to liters per square meter per hour. But if you look at these particular units using the RT there, as RT being in meters, transmembrane pressure being, let's say, in pascals, then you're going to end up with seconds. So I don't want to confuse you here, and that's why I'm saying let's not worry about those. Let's just worry about the fact that a flux is volume per area per time, or you could also convert that to distance per time. And with these particular units here, the RT and the mu, you're going to end up with kilograms, meters, and seconds. So unless you convert away from the seconds there, then you're certainly not in hours. And I went on to derive a little bit using pascals themselves. So if I had to remind myself, and maybe I was in the middle of doing that when the internet cut out, but a pascal is a Newton per square meter, and that's equivalent to a kilogram per meter per second squared. And so if we put that unit back in for the transmembrane pressure here, just to the kind of a units analysis here, we'll see that what we've got is this pascals per 1/meter per kilogram per meter second. And so when we put all that in, we end up with our flux being in cubic meters per square meters per second. So it should all work out. Units should match at the end of the day like that. And all this was just deriving from, okay, what is a pascal, and what does it take to get from that to like terms. So don't worry too much about that. I was just elaborating on the units there and how that works, and explaining why what I wrote there I probably should not have written. In fact, if you don't mind, I'm going to edit that real fast so I don't have the same issue next time I teach. Okay, so now we could maybe look at it, but okay. Anyhow, membranes, generally, if we were to take a look at them, almost every membrane is going to have a kind of two features. First of all, the separation layer, so the very thin component that's actually preventing small stuff to get through, and then a support layer that's acting as a, kind of a layer that's not doing any separation. We don't want anything getting stuck in that layer. We want water to flow as freely as possible through it, so it's going to be very permeable as much as we can, but it's going to keep a structure and a support system for the separation layer, so that the separation layer doesn't experience any breaks or cracks. The pressure with particles encountering it. So here's a few electron micrographs that show it pretty well. You can see here the separation layer, very thin, very fine pores there. You can kind of barely even see them at this magnification, but the rest of it looks kind of spongy, like water can kind of flow in and out this area. So that's sort of the idea, and you'll see that repeated again right here, these wide cavities and a thin layer on top. The reason we do this is because we really want a small distance for our pressure to go across. If we go back a step and look at our flux equation as it relates to the pressure and the resistance, this resistance term, RT, that total resistance, the units are per meter. So this is some description of how much resistance is the water encountering per distance it's going. So it's really the water is getting slowed down, lagged, whatever you want to call it, as a function of how far it has to make its way through that, which will be obvious when you think about it. But for a membrane, if you can reduce that down to very small, we see here again a fine layer here, small pores, and then much larger pores below, water's going to flow through much quicker. So we have lower resistance there, and then our bottleneck is just the separation layer. And the other thing, I think I mentioned this last time, when we operate a membrane, we're definitely going to want to operate it so that particles, the flow direction is like this, where you encounter the separation layer first and not the support layer first. That way, particles will get stuck on the outside of the separation layer and be able to flow away with the whatever retentate stream we have. If we were operating the other way, they may well get stuck inside that support layer and start clogging it up pretty bad, where it's hard to remove that. Another thing to consider as we operate a membrane, which is pretty much universal for membrane operation, is fallowing. Junk gets stuck onto the filter. The stuff we're trying to remove is removed, but where does it go? We'd like to just wash it all away, but sometimes it starts accumulating. In fact, all of the time it starts accumulating some fraction of it, and sometimes we get microorganisms involved. But essentially, what's going to happen is there's going to be a layer of particles depositing on top of a membrane. Then, as we keep filtering, we're often going to have more and more layers to the point where we get what we would call a cake. So we're doing then cake filtration through that cake of foulants that are acting like a membrane or a separation layer themselves. So that plays a role when we start talking about our resistance. If we want to know something about how much resistance we have in a membrane, we can actually talk about it in a couple different ways. Generally, the big picture is we have a total resistance. That's what that flux equation showed a moment ago. We said the flux J is equal to that transmembrane pressure divided by the resistance, the total resistance encountered times the viscosity of water, or the fluid, right? So that total resistance is really essentially what matters most. And then we could break that total resistance down into a few components, including just the membrane itself. What is the innate resistance of the membrane? We would call that Rm. And I made this nice little drawing. You can see, I can't erase it at this point, but the membrane resistance is really just ideally coming only from the supporting layer. So I kind of made a green layer here. So just the support layer, or excuse me, just the separation layer. The support layer may add a little bit, but depending on how things are designed, ideally it should just be the separation layer that's providing the resistance. Then we could have what we call fouling resistance, which this would be kind of generic fouling and not the cake fouling necessarily is what we're referring to. So as we have particles filtering through, some are making it through, some are small enough, so maybe it's organic matter just kind of accumulating. Whatever's happening, stuff is going to slowly line the walls and start blocking pores in different ways and shrinking the pore sizes so the membrane has more resistance because of the fouling. So that's what we mean by RF. And then the last component would be the cake layer resistance. It's still a form of fouling, so don't get too confused here between the RF fouling and the cake layer. But this is really stuff that's added on top of the membrane that's acting like another separation layer all on its own. So that's the difference there. And all this really is going to show the importance of membrane cleaning. Before the exam, we talked about granular filtration, and the whole deal was really about how often do we have to take the systems down to clean them. Well, in membrane filtration, it's similar. Controlling the fouling really determines the flux that we can operate at or the pressure required to operate at a flux we need to, right? So in either way, if we're controlled, a lot of times we want to have a constant flux, then we're going to have to ramp up the pressure up and up and up, and our membrane better to be able to handle that. Otherwise, we could have some breakage. So we have some operating limits, and obviously it costs more if you increase the pressure. So membrane operation then is driven in large part by managing the fouling. So how often do you backwash? How often do you do a full chemical cleaning? A lot of times it'll be a backwash every 20 minutes just for 30 seconds, right? The time scale goes a lot quicker because it's a little bit easier to just reverse direction in a pressurized system and pipe that water away than it is to do so for a large granular media filtration system where you have to purge stuff that's all throughout the system. So it's essentially faster and more frequent compared to granular filtration. Okay, so we could potentially look at a problem where we break the total resistance down into different components. Maybe we would look at a problem where we had some amount of total, some portion of that's due to the cake layer, and then we double the cake layer resistance. All that's doing is we're saying, okay, well, we did have this, and now we double that cake layer, and we have a new value, but it's just a summation, right? It's very simple in terms of understanding the resistance. It's just the sum of the resistances. So any problem we deal with a resistance is going to be pretty straightforward. just going to have to make sure we're in per meter units. And these are usually very large because if you think about it, the per meter, you don't have a full meter of a membrane, right? That would be a very, very large distance unnecessarily so to push water through. So if you're looking at the pressure divided by essentially a per distance resistance, if you have a very, very narrow resistance, the pressure and the flux numbers come out reasonably if that resistance is very large on a per meter basis. So you'll see when we do some problems, R of T is often 10 to the 12th or something like that per meter, plus or minus a couple orders of magnitude. But just be prepared if you do solve a problem like this and you're freaking out that 10 to the 13th per meter, that sounds weird. That's actually typical for this type of problem. Okay, so I wanted to talk just a little bit more about the types of fouling with this picture and introduce another concept similar, the permeability. So another relationship we can make between flux and pressure is what we call permeability, or LP. And we'll say that the permeability is equal to the flux divided by the pressure. So if you think about different types of soils, you've probably learned about that. Sand is going to be very permeable, clay's not so much. And you can kind of think about that in terms of, if I pour some water onto the soil, what kind of flux, what kind of flow are we getting through some area of that water, given that it's got gravity pulling it through, let's say. And you're probably not going to get clay allowing anything through, whereas sand, it'll permeate right on through. So it should be a kind of a familiar concept here. There's not a whole lot to it other than just defining it that way. And the units here then would be, if TMP is in pascals, would be meters squared seconds per kilogram. So again, that's permeability is flux over pressure. And here's a few more examples of the fouling that we might see that would be limiting the permeability. So if we were to reduce this permeability value, you can see that that ratio of flux to pressure is decreasing. So we need more pressure to get the same flux if we have changed the permeability, right? So if we completely block the pores, the pore plugging or pore blocking, then we're literally reducing the number of pores that water can go through because they're blocked, or maybe just a very small bit of water can go through. So that's one method, or one, mechanism of blocking. And we have what's called standard blocking, where that's kind of what I was trying to depict for the fouling generally. The resistance due to fouling was kind of the fouling that happens inside the pores and on them and around them, just generally constricting the permeability in that manner. We have another one called intermediate, where we're starting to form some bridges over, and we have the insides starting to be covered. So there's a little bit of blockage of the pores, but not necessarily cake filtration. And then there's that completely separate mode we would call cake filtration. And the reason these are distinguished is because if you look at the pressure versus flux profiles when operating a membrane, once you hit the cake filtration, those relationships change. So at some level, you're just ramping up maybe linearly, and then suddenly you hit that cake filtration, and then you've got a little bit more exponential, something like that. I don't remember the specifics, and that's, there's a lot of research going on about all that, but that would be the reason to separate them, because that's going to tell you, okay, how much increase of pressure do you have to have given which, the regime of fouling that you're in, is going to dictate that pressure flux relationship. And so if you then would probably want to operate your membrane and have a backwash system in place that's accounting for that properly, or expecting that. Okay, so with that, I wanted to give a practice problem. Here we have several part problem. We have operators of a small groundwater cleanup decide to implement a cross-flow microfiltration membrane unit as a pretreatment step to ensure that the influent groundwater does not contain any large particles which may clog the other treatment steps. So a simple membrane system, it's microfiltration, so that's actually fairly large pore size. The system must treat 200 liters per hour. It utilizes a membrane with a pore size of 2 micrometers and must recover at least 95% of the water. The influent water contains 30 milligrams per liter of particles, and the membrane rejects 85% of it. Label the feed, permeate, retentate streams on the diagram, and then part B asks, what is the concentration of particles in the permeate? Part C asks, what is the concentration of particles in the retentate? And then finally, D asks, if the membrane is rated for a flux of 25 liters per square meter per hour, what total membrane area is required to meet the flow demands? So I'm going to give you a few minutes to work on that. I'll remind you real quick that some of this information, we were given the water recovery rate. So that water recovery, I think that's lowercase r, but I could have them backwards. So we have two different r's, the recovery and the rejection. And these are dealing with the water or the liquid and the solute. So in terms of the efficiency, we're looking at two different things. For the water, this was the amount of flow that we actually produce that's clean and usable over the amount of water that we're supplying to the membrane, the feed. So the recovery then would look like that. And the rejection, of course, is going to be the fraction, a fraction concentration-wise, how much is rejected. I'm just going to skip back up to the slide so I make sure I'm not confusing anybody, not trusting my memory at the moment. This is, so 1 minus, so this uppercase R, fraction rejected, 1 minus the concentration in the permeate divided by the concentration in the feed. So this is what we covered at the beginning of last time. So just kind of reminding all of us here. So 1 minus Cp over Cf. So concentration in the permeate times, or divided by the concentration in the feed. And of course you can add the 100% if you wanted to go from fraction to percent. Okay, so with that, go ahead and give this a shot. See if you can solve that system. All right. So, first with the diagram, fairly simply here, we have the Q feed in A. B here would be our Q retentate. And then our permeate we could describe with either D or C. Either one's fine because remember, it's really whatever passes our barrier there is what we're talking about. So that's kind of the schematic, is whether or not something's crossing the membrane barrier. That's determining whether it's been QR or QP. Okay, so for part B, we're asking what is the concentration of particles in the permeate stream. Well, we know that 85% are rejected, so simply we probably could just say, well, what's the concentration in the feed? And you know, if we had this, if it was just straightforward, we could just say, well, that's exactly the 85% of that is, or 15% of that's what we've got in the permeate. Well, let's go ahead and say the R is 0.85. That's equal to 1 minus CP over CF. So we make sure we do it right. So we can rearrange and say CP over CF is equal to 1 minus 0.85 or 0.15. So CP is going to be, like we could have intuited, 0.15 times the concentration in the feed. So the feed contained 30 milligrams per liter. So CP is going to be 0.15 times 30 milligrams per liter. Grab a calculator for that. So 4.5 milligrams per liter. Okay. There's definitely potential to accidentally overcomplicate problems with regards to membranes. Of course, sometimes there will be some calculations required, but make sure to be looking for what really is being asked and how can you approach that from what's given. So part D says, what if the membrane, wait, was that? Oh, sorry. So that's the permeate. Part C asks, what is the concentration of particles in the retentate stream? So that's going to require a little bit more of a mass balance. And then part D is going to ask if the membrane is rated for a flux of 25 liters per square meter per hour, what is the total membrane area required? So for the concentration CR, it's going to require a bit of a mass balance. We know that we have conservation of the mass, right? So we're going to have the QF times CF. That's the total mass entering that chamber. We can do the mass balance, by the way, kind of on this box, right? We could look at it as the mass coming in or out of that control volume. And that'll give us a way to deal with it. So the QFCF is really going to be equal to whatever's leaving from the permeate plus the retentate. So that's going to be, in total, the mass balance. Now, membranes are very handy because we can actually manipulate. Normally if you have a pipe flowing and it splits into two ways, they're going to be the same concentration regardless. Membranes are neat because we can actually tweak that and adjust it at, causing more to go one way than another. So, given that, we know that our flow rate, this QF, so let's write out what we know here. QF is equal to 200 liters per hour. QP, we're not sure of, except that we know that we're recovering at least 95% of the water, right? So then we could solve for that. And that's going to be 0.95 times QF. This is coming from our equation we wrote out a minute ago, that the recovery, the water recovery, that 95% is going to be equal to QP divided by QF times 100%. So if we say 0.95 is equal to QP over QF, and we know QF, we just multiply QF from both sides and we solve for QP. Very, very simple there. That's all I was doing. Just making use of that. And honestly, that is intuitive. I'm giving that equation to you. I'll give that to you on an exam. But it is very intuitive. So make sure to be double checking with yourself kind of on that intuition side of it. So 95% of 200 is 190. So QP then is 190 liters per hour. That leaves us with 10 liters per hour available for the retentate stream, because we're not losing or creating any water here. Okay, so that's our flows then, and we should have enough information now to solve that mass balance. So it's the QF, so 200 liters per hour, times the CF, the concentration in the feed. That was 30 milligrams per liter. So I'm just taking this. And that's going to be equal to our 190 liters per hour times CP. We solved for CP. That was 4.5 milligrams per liter. All that plus our 10 liters per hour times what we're solving for is CR. Okay, so I'm gonna pull up Excel real quick, make that easy. So let's take 200 times 30. I'm going to subtract the QP, CP from both sides. So subtracting 190 times 4.5. And divide all that by 10. So our concentration in the retentate then should be 514.5 milligrams per liter. And as a mental double check, you should expect that this is going to be a lot higher than what you had in the feed, right? If you got a number that was lower than what's in your feed, you know immediately something went wrong, because you're having a concentrating effect here. So CR is 514.5 milligrams per liter. So that's part C. And on to part D then. Any questions, by the way? Any issues? Okay. So part D, we're asking what is the total membrane area. And the membrane area This is going to be related to our flux. We know that our flux is a flow rate divided by area. So very simply, you might be thinking to yourself, oh, I've got a flux, what's the pressure? But you might not even need the pressure, right? We can do calculations between flux and pressure, but in a problem where we know the flow rate and we know that we have some desired flux, we can use those pieces of information to solve for our area. So area then would be Q over flux. Now the Q here, this is the Q permeate, right? The flux across a membrane is described by the amount of water that actually gets across the membrane, right? This is not the Q feed. So keep that in mind when you solve problems, that the flow rate that we're talking about is important. So this is actually going to be QP. So this is going to be 190 liters per hour divided by the flux that was given, which was 25 liters per square meter per hour. And we can solve that. Those units should come out where the liters per hour cancel and the per square meter comes to the top. And so that gives us 7.6 square meters. Does that make sense? So I'm just going to write a little note, use QP for the flux across a membrane. Okay. Some more space for that. All right. So unless there's any other questions, move on and get started with the disinfection component. Okay, and I'll update that file online with the current one now that we've done that. All right, so I like to talk about disinfection in terms of, I like to get us started in terms of sterility versus disinfection. So who believes that the water in my bottle has been disinfected? Presumably, right? I got it from a water fountain or something, right? Something from a tap. So hopefully it's been disinfected. Now, who thinks then that this is sterile water? Okay, so a lot of you know better from being in kind of environmental systems. You often ask this with the civil engineers, and a fair amount of them like, well, what's the difference? It should be sterile, right? Well, no. Actually, there's going to be millions, if not billions, of microorganisms that I'm about to drink. Pleasant thought, right? So sterility is when we're describing the case where any organisms, whether or not, either they're not living or they're otherwise unable to replicate, right? We would call certain hybrid animals, donkeys, for example, as sterile or sterile because they cannot reproduce. They're not able to bring offspring based on their gametes and all that, biology, right? If we cause an organism, a microorganism, to no longer be able to replicate because we damage its DNA, perhaps it's still functioning and living, but it has been sterilized, right? So it's not actually a complete destruction per se, but that's a very different definition regardless than what we say when we're talking about disinfection. Because disinfection is really removing or sterilizing microorganisms to a point where there is no longer an infectious concentration of them. So we are getting them down to avoid infectious levels of pathogens. So that means we can drink water with, the worst viruses and pathogens and whatnot, so long as there's not so many that it's going to cause an infection. In fact, if I'm drinking a liter here, and I do so over the course of half a day, and there's some number of pathogens in there, we can consider that, well, that might be all right, so long as there's not so many that they're going to make it past natural defenses, or just kind of the natural variability, how many is required to cause somebody to be sick. So I want to come back and talk about that in a minute, but just kind of as a show of it, disinfection is almost always coming right just past our filtration of some sort. We're going to talk about water softening, which I have not done a unit on that before. We'll talk about that after disinfection. That's, I believe, would normally, sometimes it might happen before disinfection actually. So we might have water softening here as another step, but essentially disinfection is last or almost last, right before we send it out. And I say almost last because I think it's going to matter a little bit based on pH, what pH we want. In fact, we might do some of the softening beforehand, and then we adjust the pH for disinfection, and then we polish the water afterwards. That polishing step is usually describing making sure that it's the right hardness, it's got the right amount of residual chlorine, and it's got perhaps fluoride in it to trace the distribution system and provide that health benefit. So essentially, we are towards the end of a typical drinking water treatment train. So the next couple of topics are really going to be dealing with those spots. Occasionally, some treatment plants might try to pre-chlorinate a little bit. I think we had an example problem, not sure if that was this class, maybe with ozone or something. There's a bit of a worry about disinfection byproducts. Well, one thing we want to do during all these steps, and including filtration, is to remove precursors for disinfection byproducts. So removing organic matter, stuff that could react with our chlorine and create hazardous chlorinated compounds. We don't want that. So there's a few things to consider here and a few reasons why we keep disinfection last. And if not for the disinfection byproducts, certainly we don't want pathogens being able to hide in and behind particles. So particle removal is actually quite important for disinfection. Okay, so talking about disinfection, how do we know what is an infectious level? Does anybody know how we would know the infectious level of norovirus or coronavirus, for that matter? We're not typically concerned about coronavirus for ingestion hazard, although that it may well be able to give you the GI symptoms. It does have a GI component to it. But talking about water, we're normally talking about waterborne diseases, norovirus, rotavirus, or bacteria. We could do cholera, E. coli, et cetera, et cetera. Does anybody know how we measure that? So it's quite entertaining, actually. So I had a chance to take a couple of classes at Emory during my graduate school, and they had some speakers from the CDC come over to talk about kind of public health side of microbiology. And what I learned was they do human experiments on volunteers and say, okay, we're going to pay you $1,000 to come stay in our little hotel hospital thing for a week. We're going to feed you exactly what we know is good, clean food, so there's no other confounding factors that you might get a foodborne illness from. And then we're going to give you a pill. And if you're lucky, it's a placebo. There's nothing. Or if you're lucky, it's a small dose, you may have an asymptomatic infection. Or even if it's a high dose and you happen to be asymptomatic, good for you. Otherwise, you're going to be sick here for a week, and we're going to keep you as healthy and happy as we can, and you will have earned your $1,000. So literally, they just get a bunch of volunteers, probably college students, grad students, young healthy people, happy to spend a week, holed up studying, right? Exactly. It's like, who wouldn't? So kind of funny, but they actually do that, and then they would vary the dose giving to people. So I just can imagine like signing up for something like that. Like, all right, fingers crossed, I got the low dose with the placebo. So anyway, certainly I don't think you can do that for all diseases, but for many of the ones that you have pretty good protection and treatment for, you could do that. So it turns out that for some things like a norovirus, it only takes, tens, maybe hundreds of virus particles to get you sick. And viruses tend to make lots and lots of particles, so it doesn't take a lot of this of noroviruses to get you sick. Probably be somewhat similar to rotavirus. Poliovirus, by the way, is another food and waterborne disease. And essentially, what we're talking about with food and waterborne disease, coming back to that fecal-oral route of transmission, almost always it's stemming from a gut infection, and somehow that makes its way back into somebody else's food or water. On the bacterial front, cholera, you've probably heard about it. Did I already tell you about the ghost map, or have you heard about it? Okay, so I think I'm going to talk about that in a minute then. So Vibrio Cholera, infamous for the cholera plagues. This actually requires quite a lot of bacteria because it's very sensitive to acid, and our stomachs tend to have a lot of acid in the stomach component. So the cholera bacteria have to make it past the stomach and into your intestines before they can really survive and thrive and cause an infection. So these actually take something like 10 to the 6, so 1 million at least, to give an infection. Now, their way of operating, they do produce quite a lot of cells, so they can certainly do that. And if you're at all familiar with cholera, the way the disease works is essentially it takes your intestines, which are normally pulling water out of your food and out of whatever's being processed, so it's pulling water out and into your bloodstream. It actually reverses that process, causes your cells to do the opposite, and pulls water out of your bloodstream and into your digestive tract. So the big risk for cholera is dehydration. Now, fortunately, that's a simple risk, and nowadays we don't really have a big problem for it if we have access to proper hydration salts, IVs, stuff like that. For anybody that lacks that, it can be lethal very, very quickly. So back in the 1800s, which is really one of the first times we learned about waterborne disease in the first place, with cholera in particular, the lethality was very, very terrible. And with cholera in particular, it happened very quickly because you can't live very long with, in that severe dehydration state. So you'll dehydrate in some cases within a day or less, and die. So it's a pretty serious issue if you don't know what to do with it. And one of the byproducts there is that's a lot of excrement that's created very rapidly and can spread the disease rather effectively from the disease standpoint. E. coli, salmonella, things like these are often more along the thousands to maybe tens of thousands or so. Something like that. I don't remember specifically, but there's some variability here in terms of how many of the organisms does it require to get you sick. Now, this is talking about foodborne infections. If we're talking about food poisoning, you probably have never really thought about a difference here, but food infection is what you probably think of when you eat something and then later that night you're starting to not feel so great, or the next day and you're like, oh shoot, what did I eat? A food poisoning is actually when some microorganism, could be E. coli, some species, or salmonella, or botulinum in the worst case scenario, have produced a toxin. And it's actually a poison that's in the food then, because the bacteria or organism has been spending some time creating it, then you're almost immediately ill after eating it. So that's what we, technical term for food poisoning, is distinguished that way. There's another category of organisms, and part of the reason I'm talking about to this level of detail of these different organisms is because in order to do proper disinfection, we need to understand how many is going to take to get us sick, and how easy is it to kill them, right? So kind of the nemesis, at least for typical like chlorination, would be our protozoa. So Cryptosporidium in particular, we had the paper on that, the Cryptosporidium outbreak in Milwaukee. These are pretty resistant to chlorine, or they can form cysts that are, and they really only take something like 3 to 5 cells to get somebody sick. So it doesn't take a lot, and they're very resistant to chlorination. Ozone does a pretty good job. UV does a pretty good job. So chlorination is not always the way to go, or at least you have to be mindful of this. So that's kind of one aspect that we might control for, right? Let's make sure that we can reduce these by 99.9% if we expect, we have to have some knowledge about what we expect coming in. If we had billions of these coming in, we would need to remove quite a lot. Fortunately, they're not produced in as high quantities as, let's say, cholera. So at the end of the day, dose makes the poison, holds true here. Dose does also make the infection. So that's an important component of our disinfection strategies, making sure that we are not, maybe there's a few pathogens in here, but I'm pretty confident that there's not enough to give me an infection, right? That's the important part. Okay, so this brings me to Jon Snow. But this one did know something. I do have a brother named John. He maybe fits the bill of not knowing anything a little closer, at least in my opinion. Game of Thrones reference there for anybody curious. Jon Snow is called the father of epidemiology for tracking an infamous cholera outbreak in London. So back then it would be kind of the plague, right? The plague struck in near Broad Street in London, and ultimately what he did was he tracked it to a water source. It was the Broad Street pump that was supplying contaminated water. And this is the first time anybody really, like the germ theory of disease was just starting to catch on, if at all. And what he did was he made a map of who was dying in this area. And it's a very morbid thing to do, but with the craziness of such an outbreak that kills people so quickly, that's got to be really scary, right? So it was very urgent to try to figure out what was going on. And the map that he made is referred to as the ghost map. There's also a book. It's a literary adaptation of the historical account, so they filled in some details to make it narratives in form. It's a very good read, enjoyable, interesting, and informative. And so if you ever visit London, you got to go visit the Broad Street pump. Essentially, he stopped the outbreak by removing the pump handle from that pump. It turns out that there was an infant that got sick from some other, I think they had traveled. So an infant was taken, traveled from someplace else, brought the infection there, and was living in this house right above the Broad Street pump well. So essentially, without very good sanitation there, their sewage was seeping down into the well for the Broad Street pump, which is not good in the first place, but pretty awful anyway. But the deal was, since it was an infant, and the digestive tract is different, the infants are actually, while vulnerable, not so prone to dehydration, or whatever's the working with the disease. The infant stayed alive for several weeks. And may have even survived. I don't remember, but was not a quick death for the infant. So it was actually a continuous production of Vibrio Cholera contaminating the well at that spot. And so if you look closely at this map, you'll see kind of dark bars, and I've got another picture to show better. But each dot represents one death in the house. So as you get longer and longer bars, that's more deaths per house. So kind of insane to think about, but within the span of a few days, there were tens, if not 100 or so. I think there was more than 100 deaths, and so some houses would just be completely ravaged and very terrible. You can see it a little easier plotted this way. And so he took this map and then also identified where the different pumps were. This is all based on a little bit of a hunch. He thought he saw something through a microscope in the water and thought that he had identified the disease-causing agent. It's likely that he did not have that level of detail, that level of magnification, but the theory turned out to be, or the hypothesis was correct, even though the observation was misleading, right? So there was a disease-causing agent in the water, and if you can see, there is a flag right here. That's the Broad Street pump. So each flag represents a well. That's the Broad Street pump well, and that's really the source of the outbreak. So people passing through, getting water from there, maybe it was somehow less convenient to get to this well, or somebody worked that way and brought it up here anyway. Maybe they, whatever reason, it's possible secondary contaminations, but that's the story of the ghost map. It's definitely morbid, but also fascinating. And so that's mapping the disease like this, tracking rates, is really what epidemiology is about, which is the field my wife has worked in for some time. Okay, with that, we've got 5 more minutes, so I think I'll end there and we'll pick up on the disinfection strategies next time. Again, it will be a virtual class next time, and I posted midterm grades today. That does not include the participation score. I have not gotten to that yet. I just need to collate all that together. So I'll give an update on that, and come grab your exam if you don't have it. Okay, so I'll see you guys online on Thursday.